Good morning again. When Xiaowen asked me if I would be willing to introduce the keynote speaker this morning, it was a no-brainer. It has been a while since I got to meet Dan Atkins, a role model and a mentor of mine. I have been at the University of Michigan for 20 years, and he has been there 40 years. So when I grew up, I got to know him, and I really admire him. So it is a pleasure for me to introduce Dan Atkins from the University of Michigan, where he is the Kellogg Professor of Community Informatics. He is a Professor of Information in the School of Information and a Professor of Electrical Engineering and Computer Science in the College of Engineering. He has also served as Associate Vice President for Research at the University of Michigan. So most of you in this community probably know Dan as chair of the NSF's Blue Ribbon Advisory Panel on Cyberinfrastructure, which in 2003 issued a landmark report revolutionizing science and engineering through cyber infrastructure. This report is referred to by many as the Atkins report. It outlined the evolution of cyber science and the opportunity it affords our nation to lead the world in 21st century scientific discoveries. The Atkins report recommended a major program in cyber infrastructure, enhanced science and engineering research, under the leadership of NSF. And therefore, when NSF looked for the inaugural director of the Office of Cyber Infrastructure, it's no surprise it tapped Dan Atkins. Most of you, like me, are also familiar with the fast lane at NSF. Dan Atkins was the director of the NSF Express project that led the foundations for Fastlane. He has directed several large interdisciplinary NSF projects that led to the development of the principles for design and evaluation of co-laboratories, or centers without walls. So this morning at breakfast, I said to Dan that, Dan, I'm going to introduce you and I have 6 pages. He said, come on, don't embarrass me. So I only have 2 more paragraphs, Dan. Dan has made major contributions in high-performance computer architecture. He has led or participated in the design and construction of several experimental machines, including some of the earliest parallel computers. He has led industry and university work in collaborations that created special purpose architectures, and also he collaborated with Mayo Clinic on the development of computer-assisted tomography. Dan Atkins is the founding dean of the School of Information at the University of Michigan. He formed and directed an Alliance for Community Technology, ACT, that was sponsored by the Kellogg Foundation. He serves as a consultant to many foundations, including the Kellogg, on the innovative use of information and communications technology. He has worked for many institutions developing cyber learning opportunities, which he is still very much engaged in, for enriching education opportunities for at-risk youth in the US, and higher education in South Africa. He is the co-author with James Dudestad and Doug Van Houweling of the 2002 book, Higher Education in the Digital Age. And finally, most of you probably know, Dan Atkins is an alum. He received his PhD in computer science and MS in electrical engineering from the University of Illinois, Urbana-Champaign. So please join me in welcoming Dan Atkins.
Okay, good. Well, Thank you very much. That was extremely generous introduction. I'll just add one more claim to fame. I'm the person who decided whether the word cyberinfrastructure is written with or without a hyphen. So first I want to say thank Dan Katz for his comments. He gave you some very good advice, so pay attention to that. I also hope, at least privately, he would tell you that going and doing a tour at NSF is a very good thing to do, and that you can actually get things done. And we, in a sense, deserve what we get in terms of us, the best people, going and serving at NSF. So at the appropriate time in your career, if that's possible, please consider that. I also, like Bob Easter, am far from an expert in the areas. I could kind of carry on reasonably coherent conversations at the poster sessions yesterday. But what I'm here to talk about and to challenge you to consider is embracing cyber infrastructure as a definitive enabler of what you're about, and also do things in a way that create benefit for the larger world of knowledge communities. I use this word knowledge community as a generic name for communities which create, disseminate, and preserve knowledge. And my notion of dissemination of knowledge includes learning and education. And I believe if you think about it, you'll agree with me that the core of a great research university, the fundamental nature of a great research university, such as the University of Illinois, is our knowledge communities. And we all live in multiple, often overlapping knowledge communities that are involved. And I think it's starting to become apparent now that learning and discovery is intrinsically a social process. And so my message to you today is that the highest and greatest end goal of these technologies that we're talking about is the facilitation of the effective work of knowledge communities. And that all we're talking about here outside is essential, but those are the bases for tools and processes and so forth that are functionally integrated into these knowledge communities. At the personal level, I do want to acknowledge that I got my career started here. I came here as a graduate student back in 1965. ILLIAC 1 was decommissioned at that point, but the university computing facility was ILLIAC 2, one of the first discrete transistor machines. There's a chunk of it over in the CS building, you can see. I personally worked primarily on the ILLIAC 3 machine, which was sponsored by the Atomic Energy Commission as one of the first massively parallel machines of the day with special image processing capability, cellular autonoma for bubble chamber tracking. As a byproduct of that work was that I helped develop the so-called SRT division algorithm that you use every day in your laptop if you do a division operation. And unfortunately, ILLIAC 3 burned up just a few weeks before it was going to be turned on. A tech left a soldering pencil going at night and it got into some paint. And so literally that went up in smoke. Fortunately, my thesis, which at that time, of course, was on paper and not backed up a million places in the cloud, did not go up in smoke, although there was a fireman's footprint on the top of it as I laid on my desk. So, and then I had a little bit to do with ILLIAC 4. And so the first part of my career, first decade of my career, I was a computer architecture. But as computing and communication came together, I started to see that the ultimate goal was going to be in providing new modalities for people to do knowledge work together in ways that could potentially dramatically relax constraints of distance and time. And a group of us at Michigan also appreciated that to reap the full benefit of that possibility, we needed to start thinking about this not as purely a technical challenge, but as a very complex socio-technical challenge. And that led then to the creation of the interdisciplinary research teams. Fortunately, Bill Wolf, who was serving as the SCI's AD at NSF, had this concept of the Center Without Walls, the collaboratory, and that provided a funding stream for the type of work that has defined the rest of my career. One thing that excites me about this meeting today, and one reason I eagerly accepted the invitation to join you and have a chance to convey perhaps some words of wisdom and some challenges to you, is the firstness of this meeting, the formative stages that you're in, where you are, as the website says, bringing together researchers, educators, and practitioners, and that blend of research, education, and practice is essential to what I'm talking about today. And then to synergistically advance the state of the art of the CyberGIS, space-time analysis, modeling, and synthesis. And my sense is that from talking to you and perusing the posters is that your notion of what this field is very inclusive, as well it should be. And then to foster international collaboration and cooperation in this area, to create the alignment of mutual self-interest that Bob Easter alluded to. So my message, my challenge, my hope for you is that as you begin this journey together, and hopefully the team will grow as you move forward, that you will become an exemplar for both what you are doing, in other words, the great science, engineering, and practice you're creating, but also for how you are doing it. And that's what I will elaborate on in the remainder of my talk. This figure from one of the websites, implies kind of the right ingredients for the kind of knowledge community initiative that I'm trying to describe to you. The fact that you have humans at the center is encouraging, that you have a human-centered perspective on what the ultimate payoff is. Of course, the visual and the analytics together, the distributed nature of both the resources, the data, the tools, and the people and institutions that are coming together, that this is intrinsically collaborative, that it's data and compute intensive, and that what you're aspiring to is a systematic goal, a systemic goal, an environment, not just a point product. Those of you who know me know that I cannot give a talk without using a Borromean ring, which I actually stole from Jim Myers many years ago, and I actually saw a few Borromean rings out here. The Borromean ring are three rings that are interlocked in such a way that if you pull one of the rings out, it destroys the whole construct. And I've used that for many years as a symbol for kind of the fundamental synergy and alignment that's required to achieve progress on many of these grand challenge socio-technical aspects. This is a slide they actually used a lot at NSF of how we need to enhance a culture of mutually benefit, balancing participation and synergy between, I must have used this slide in Europe because I refer to it as e-infrastructure, provisioning, research application, and e-science or e-infrastructure innovation. And that this alignment and getting the Borromean ring structure going is at least my concept of what the Office of Cyberinfrastructure is all about. It's also you need a culture like this within this knowledge community you're building. And to reflect again on Dan Katz's comment about how encouraging it is to hear presidents of universities even use the word cyber infrastructure, because it's ultimately going to be the great research universities that where the rubber hits the road and where the full beneficiary. And NSF can sanction and provide some support for the kind of alignment and initiative that it takes to create these environments, but ultimately the research universities are going to have to step up to the task. So this is to show that in fundamental nature between achieving transformative applications to enhance research, learning, and societal engagement, provisioning to create, deploy, and operate advanced e-infrastructure or cyber-infrastructure, and the necessary research, fundamental research, to provide both the technical and the social behavioral enhancements in these future environments. And so at a smaller scale, this is the kind of alignment that I hope this community can achieve. Also notice on the green side that I'm advocating that as we think about creating infrastructure, we think explicitly about multi-use for this infrastructure, not just serving the research needs, but serving the associated learning needs at all levels. And also thinking about how these environments could support rapid response to unexpected emergencies or situations. And to think of that triad of applications at the infrastructural level, not just disjoint separate infrastructures for each of those purposes. So your research and education agenda, I would assume, includes creating and disseminating understanding, the basic goals of research, creating tools for yourselves and others to use in your work, and hopefully to help mitigate or even solve major societal problems using the tools and processes and knowledges that you developed. And of course, implicit in all of this is that you as faculty members, as researchers within academia or private sector, need to personally prosper, need to achieve recognition, promotion, tenure, and so forth, and therefore need to do these things within the kind of cultural norms of the institution and the reward structure of the university, which typically stresses kind of individual accomplishment, which to some extent mitigates against the collective good enterprise I'm talking about. So part of my message to you today is that I fully recognize, having been a dean for many years, that you have these personal goals that you have to achieve, particularly as junior and mid-career faculty. But as you do achieve the increasingly rare status of a tenured faculty member, and if you think about it, that being in a position where you virtually cannot be fired in today's world is a pretty unique position. And it carries with it the enormous responsibility to use that position for truly innovative and transformative things, including serving the collective good. So it's the senior people out there that I hope will particularly step up to the leadership implied in what I'm challenging you to pursue today. So I'm saying beyond these first three kind of standard things, I'm wondering the extent to which you can innovate on creating and benefiting from a CI-enabled environment for your knowledge community. And towards the end of my talk, I'm going to point to a very good example of a community that has achieved this, namely the NanoHub community under Gerhard Klimek. But even more than that, I'm challenging you to consider how you contribute to such an environment for the larger world of knowledge communities to support innovation and discovery and learning. And what you are undertaking here, big data, extracting information and knowledge and even wisdom from big data, and providing visual interfaces and visual analytics has a profound implication for most any field you can imagine. And I just also, and I hope you fully agree with me, I think there are whole new notions of data-enabled literacy, of evidence-based, data-based decision-making that needs to be defined and propagated into the curriculum, starting from the earliest grades. These kinds of tools, that some of which were demonstrated, need to become routinely used by everyday citizens in managing and informing a decision at all levels. And so there's a whole new era of data-enabled literacy, GIS-enabled literacy that this group needs to help define and propagate. Now, there is something, a link on the website to something called the CyberGIS Gateway. But when I went to it, this is all I got. And I had seen it a little earlier. There were a few things there, and there were a few people. And so I just want to say that I'm not being negative about this. I'm saying that it's very fashionable these days to have a gateway, define it, or a hub, and then of course everyone adds a Facebook site and a Twitter site and so forth. I'm talking about something substantially more fundamental than that, but I am kind of using this as well. You've got this kind of aspirational statement here, but this needs to be made real. And of course, the hard part is not filling up a nice glitzy looking web page. The hard part is becoming a fundamental part of the way the world works, of where people achieve personal benefit and a reward structure that rewards the kind of collective activity that I'm advocating. So I want to share with you why I'm so passionate about this notion that the overarching goal is not just high-performance computing, but high-performance collaboration. It goes back to the collaboratory work that Bill Walsh helped enable, and a project known as the Michigan Upper Atmospheric Research Collaboratory. And this started in the mid-1980s when a group of space scientists that studied the magnetosphere, and all of us have had these encounters of meeting people at remote places like Champaign-Urbana that have had a little conversation and then figured out there's a lot to do together and changed our lives. And in fact, it's been a real ego trip for me here, because several of you have come up to me and say, you gave this talk back in blah, 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 and you said this and you said that, and I followed up on that, and that really became this and that. And so that's really, that's great to hear that. So there's a large incoherent scatter radar antenna up in the southwest coast of Greenland, a place called Sonderstrom. And they would use this to study the solar storms, the interaction of the solar wind with the magnetosphere, the thing that brings us the aurora borealis, but also brings us crashed communication satellites every so often. And they initially were looking for what would they call a telescience, just the ability to control these instruments remotely over the internet. And back in those days, just that in itself was a major challenge. Well, we got funding from NSF, which ultimately led to the creation of a collaboratory which supported real-time data gathering campaigns. And we built this environment, by the way, with the Next computer, Steve Jobs' intermediate project, which is really the basis for OS 10 now. And that ability to do rapid prototyping in an object-based environment was actually part of the great success of this project. And so this was a window which gave real-time display and visualization of these various data streams coming from various instruments at Sonderstrom. And it provided an interface to dynamic workrooms where people could break out and do chats. It had team chat, and chat was the primary modality of interaction at that point, in part because of the bandwidth limits. It had archival data, had access to journals. It had a concept of session replay, where all these streams were being captured, and the control of the data gathering was migrating around the world during normal business hours. Different teams were in charge of the overall experiment, but then people could wake up the next morning and go back and scan the chat and other things, and if an interesting phenomena had occurred, they could go back and replay that session. That session could be annotated and stored and revisited at other times. And perhaps one of the greatest contributions of this project was what the people in that research community, like Tim Killeen, came to call data theory closure. And it was quite amazing to me at that point, and I think we still probably have too much of this going on in other fields, that the people who did experimental work in this arena and the people who did theoretical and modeling work in this arena rarely talked to each other. And one of the, I guess, fairly profound byproducts of this is that, I forget which is which. One of those figures on the top, I think the one on the left, is actually being generated in quasi-real time from the experimental streams coming in from the instruments. And it's showing kind of the solar storms. And the model, the figure on the right, is actually a predictive model being driven by the boundary conditions coming from there. And so they could use the predictive model to actually steer the instruments to continue to more optimally track the storms. And that's, which seems like a trivial and obvious thing to do today, took 4 or 5 years. And in part to develop the trust and the mutual self-interest that we've talked about several times. Also, prior to this point, these various ground-based observatories were kind of points on the Earth that were looking at various regions, and were in a kind of a non-healthy competition with each other. And one of the reasons the NSF funded this work was to create the impetus to build a shared chain of data, a distributed network, sensing network. And again, you may find that very difficult to believe that that was an innovation of the time, but it was. And so it ultimately led to a global set of instruments as opposed to a set of competitive, isolated instruments. So let me, and we also showed, we had a group of social scientists working on this project that indeed showed that tightly coupled intellectual enterprise could occur over distance. And this, of course, was back some years ago. So here are some of the bottom line, the little vignettes, the anecdotes that came out of this, that from which I saw the glimmer of new ways of working in many, many fields, and which provided the impetus and excitement for me to kind of move from, you know, yet another experimental machine to this world of collaboration systems. So we achieved the sharing not only of the instruments, but of the expertise of the instrument designers. And prior to that time, if you wanted to use one of these ground-based instruments, you would need to go to the group that ran it and convince them that you were worthy of using this. It's kind of like the old days of mainframe computing. There were the priests from the temple, and you go there with your cards and kind of humbly beg them to run it for you. And but as we created a chain of alternative and created a kind of a market where people could go from one to another if they weren't getting the cooperation at one that they needed, there was actually a flip at one point where people were eagerly recruiting customers, and they could remotely not only let you use the instrument, but they could help you use it and explain it. It's, for some of you at Illinois, that was one of the cool properties of this bug scope project that was here for a long time, where young kids could use the electron microscope, but not just the microscope. They'd get the expertise of someone who knew how to run it, and then if they had questions about the bug wings, they could get touched with, an etymologist or something like that. It led, of course, to much more rapid response and opportunistic campaigns because prior to that, people, and rarely graduate students, researchers, would go to Sonderstrom, and that got harder and harder, having to go through Denmark and to come back and so forth. And although they did enjoy a lot of drinking of beer while they were waiting for the data, and they kind of lost some of that, I guess, with the collaboratory, they just went there and hoped that the sun would do something interesting to create storms that actually led to data. Now, of course, NOAA or others give them a warning of a solar flare, and then they could just mount up and do a campaign opportunistically. So more science, more data, more relevant data, and so forth was being captured. It also provided, there were different instruments. The incoherent scatter radar was kind of the centerpiece of all this, but there were other instruments. And so these instruments now could come together kind of as multiple eyes, looking on the same phenomena, and it created the alignment of complementary expertise. Isolated instruments became a global instrument chain. It led to cross-mentoring and training. We actually, our social scientists documented that a PhD student in atmospheric science at the University of Michigan got much more mentoring from a faculty member in Norway than he did from his own advisor 2 doors down the hall. It also led to earlier opportunities and exposure for graduate students. So as I said a minute ago, because of cost and logistics and housing and all that, very few graduate students ever got to go on these data campaigns. They got to come back and kind of do the grunt work later. So they got to participate, and they got the benefit of the tacit learning that you get, from working with others. And but they also became known in the greater knowledge community earlier in their careers. And it also led to enhanced participation and supported the concept of legitimate peripheral participation. So if you had a URL, you could just go watch real space scientists at work. It also supported authentic inquiry-based learning at the undergraduate and pre-college level. There was a graduate of the space science program at Stanford who, for various personal reasons, wanted to stay at an undergraduate school and was particularly interested in teaching. I think he ended up at Oberlin or some good school like that. But he was able to retain participation in this elite community through the collaboratory, and he was able to really enrich the teaching of earth science and so forth within his program. And then Roberta Johnson, who is now head of the Science Teachers Association in the US and so forth, created a NASA-funded project called Windows to the Universe, which made extensive use of this and with appropriately scaffolded alternate interface, used much of the infrastructure of the UARC project to make the teaching of earth science at the high school level much more interesting. It led then to distributed workshops for post-campaign data analysis, the session replay, I'll talk to other, and then the data theory closure of getting the theoretical and experimental people to actually find mutual benefit to work together. So I go through all this, and none of this you probably find very surprising in today's era, but I share it with you partly just to see the origins of my personal enthusiasm for all this, but secondly that 10, 20 years from now, perhaps you'll look back and see things happening routinely that go well beyond this, that you had something to do with initiating. So we've talked about the Blue Ribbon Panel report. I just want to comment that reports like that come about usually from someone observing that there are a bunch of threads of activity that are prospering and doing cool things. In this case, there was the collaboratory movement, and there was actually a National Academy report that came out on that. There was a kind of ahead of its time initiative at NSF called KDI, Knowledge and Distributed Intelligence. Anyone remember that one? That was one that funded a lot of the collaboratory and digital library, in other words. There was the whole PACI initiative, of course, this place being at the center of that, with Larry Smarr and so forth. The HPC, the increasing, exponential growth in the power of raw computing. The digital library movement, for which NSF deserves enormous credit for getting all that going in the right way. The grid work of Castleman and Foster, the ITR initiative, the e-science activities from the UK with Tony Hay and Taylor and others that really got out in front of us nationally. And then the whole concept of cyber science, which was being articulated in Europe, the IT and the future of higher education, including work within the OECD. And so this work of this Blue Ribbon panel was really to understand all these threads of activity and what they were achieving and so forth. And then to step back and say, now how could we harvest all of that and integrate it together and go to a higher level of abstraction and a higher level of game, okay? And that, by the way, I would encourage you to think about that as kind of a paradigm for your own personal career. In other words, at some point, what you do becomes more mature, it actually becomes more routine. Rather than just nibbling away at it, step back and look at other things that complement what you're doing and then go to the next level of abstraction and make a contribution there. In other words, today's research objects become the components of the subsystems of the next frontier. And so this report just kind of articulated that all of these things created the conditions for something dramatically new, and the whole concept of a cyber-enabled platform for the conduct of discovery. And then that report was the basis for an internal report, which basically said, yeah, we kind of believe this, and we actually want to go off and do it. And so, some of the key takeaways from this were that we were in a new age of dawn of scientific and engineering research, pushed by the progress of the technology and pulled by the expanding complexity and scale of today's challenges. The capacity is to cross thresholds that make possible a comprehensive cyber infrastructure on which to build new types of scientific and engineering knowledge environments together in organizations, and to pursue research in new ways and with increased efficacy. So that's the point, and that's the challenge that I'm giving to you, to actually make statements like that true within your particular field. The other thing about why this report achieved resonance and actually achieved impact, and many of these reports, a lot of work goes into them and they get put on the shelf and thank you and so forth, but it was the coincidence of the push of the technology, the enabling of the technology, and the pull and the need of science were rightly aligned, and I'll elaborate on that in just a moment. Now, we've seen various definitions of cyber infrastructure. Dan gave you one. Here are others. I'm not going to spend time on that, but except to say that, well, let me back up and say it's about high-performance computing, it's about data, it's about observatories, sensing, instrumentation, it's about portals, workflow environments, and interactive visualization and analysis services. But all of that, ultimately, all of that needs to be integrated into an environment, which I refer to as a collaboratory, to support modern, internationally leading collaborative research in all areas of science, engineering, arts, and humanities. And don't forget, this is not just all about hard science. The goal is to evolve and sustain a platform that provides all the functions needed by a research community, and that also enables group knowledge workflow to occur across all four quadrants of same and different time and place. The shorthand for all of that is that it needs to be functionally complete and it needs to support an all-quadrant way of working. So what do I mean by all-quadrant way of working? I'll get to that in a moment. Some of the various NSF reports use phrases like, you become one with your resources. Another definition is that it's an organizing fabric and foundation for science, a platform for knowledge work in 4 quadrants with functionally complete services. One of the bumper stickers from the report was that we have the potential to transform the what, the how, and very importantly, the who participates in research and learning. And the who participates in the democratization of participation in discovery and learning, I think, is a potential for all of this that excites many of us. And the metrics for success here are ultimately about enhancing and accelerating research, discovery, innovation, learning, and education, about increasing the intellectual cross-section between people and what they're doing in such a way that increases the probability of a transformative hit. It's about fundamental return on investment, not simply about doing something slightly faster. It's about true innovation, not just about extrapolation. So this 4-quadrant idea is just borrowed from a chart that's been around from the CSCW, Computer Supported Cooperative Community, for many years, of just a 2x2 matrix of place and time, same and different. And so the idea is that the knowledge workflow of a community can occur in all 4 of these quadrants, and that we need to start thinking about what aspect of that collaboration is done best in what quadrant. I also prefer a phrase like all-quadrant or organization or team or something to the term virtual, because to many, the term virtual implies the exclusion of the same time, same place. In some cases, it has kind of a pejorative notion or kind of a second-class citizen notion. And in fact, my view is that the same time, same place quadrant, where we are right now, is the most precious, the most expensive, and that we need to start thinking about how we use the other 3 to increase the effectiveness, for example, of the same time, same place investment. Many of you are hearing about Coursera and the notion of flipped classrooms and so forth, and of course the increasing demands for students that lectures be recorded and be made readily available to them, within 2 minutes after the class is over. The notion of the flipped classroom is simply to say that rather than using the same time, same place to have the sage on the stage with hundreds of students sitting out there, that it's best to do that in a different time, different place format, and then to use the same time, same place for smaller, more interactive kind of learning that uses the bandwidth of being together more effectively. This is a report from a workshop several years ago that I still think is well worth reading. And in fact, I encourage you to stay tuned with all of the various workshop reports that come out of NSF and to read them and take advantage of them and to use them and to cite them, because they actually give you a very good notion of what your colleagues are thinking, gives you a framework in which to see how your work fits into a bigger picture, gives you actually phrases and knowledge and ideas that you can reflect into proposals. So it's kind of a way of keeping up with the collective wisdom of what's about. And there's a series of that were commissioned by Ed Seidel when he first succeeded me. There's 4 or 5 of these reports. The ones most relevant to this field is the one from the advisory group of Cyberinfrastructure Task Force on Data and Visualization that Tony Hay and I chaired. But there's another one on the Grand Cyberinfrastructure Task Force on Grand Challenges, and I'm sure you'll find that every one of these grand challenges depends critically on the kind of infrastructure and knowledge and tools that this community is aspiring to create. And then finally, I just want to remind us, remember I said that this the reason we got resonance for this report was the alignment of the push and the pull. And so the kind of infrastructure that we're all aspiring to create and use is actually fundamentally necessary, not just nice to have, for the conduct of science into the future. So e-science, research enabled by e-infrastructure, is increasingly essential for meeting 21st century challenges due to, first, the inherent complexity, multi-scale, and multi-science nature of today's frontier science. This is a chart that I borrowed from Jim Collins, who was my colleague AD in bio when I was at NSF, just showing the orders of magnitude of both time and distance required to study the various levels of biological systems. And many phenomena have this multi-scale, multi-science need. The accompanying requirement for multidisciplinary, multi-investigator, multi-institutional approaches, often international in scope. For all these grand challenge problems, the expertise, the instruments, and so forth do not reside in one place. They intrinsically require distributed solution. The high data intensity and heterogeneity from simulations, data instruments, sensor networks, and observatories, and part of what is driving this age of big data is the incredible development in sensor technology. The increased scale and value of data and demand for semantic federation, active curation, and long-term preservation of access. I also want to emphasize that as you go forward, focus on building the concept of long-term access, of enhancing and curating into from the beginning, not as a retrospective, and also pay attention to the need for the reproducibility of science. I think that's something that we're tending to overlook in this digital age, and that the concept of reproducibility of science is at risk unless we pay more attention to it. And I'll cite some work there in a moment. And finally, the need to engage more students in high-quality, authentic, passion-building science and engineering education. And I would say there's probably very few fields like your own who have the potential to visualization and engaging interactive visual interfaces to make major contributions to learning and education and motivating more students to go into science and engineering. This is a figure from, I think, currently being used at NSF. It's just, again, stressing that we're really talking about the creation of an ecology, of an ecosystem. We're talking about an ecosystem that supports in fundamental ways collaboration, discovery, and learning. We heard a lot about the software aspects of this morning, but all of these are part of that picture. And that we need to figure out how to make this maintainable, sustainable, and extensible. So, for example, Dan's reference to the fact that we're figuring out how to sustain open source communities without creating additional burdens. I mean, that's those kinds of policy, incentive systems, social behavioral notions are fundamental to this. It's not just about the technology and the bandwidth and the MIPS and the flops. It's about all those other things as well. And I don't have to talk to this community about the new age of data, the fourth paradigm. You all know about that, and in fact, you're stepping up to actually make that true. And then just go back to this, think about long-term access and reproducibility, all of the work. I think one of the most eloquent spokespeople for this area is Victoria Stoughton at Columbia. This is one of her talks, but if you search, and there are a growing number of meetings and workshops and things like this on reproducibility within computational science. And that's, you understand, I'm not just talking about storing the bits. I'm talking about how, including new publishing models and how do you make the data, the executable document and all of that. And you are in a great position to influence that motion. The next few slides are just to emphasize that this is a global issue. These are slides from the UK, the EU. They all have similar aspirations. And this is a slide to illustrate that we've been talking about e-science. It's alive and well and going and prospering and essential. There is not too far behind, there is a growing e-humanities arena. There's e-learning, cyber-enabled learning. There's actually even people now talking about e-development and IT and development, IT for development, and all of that, societal engagement and facilitating that. If you look at all of those orange arrows, those really define the fundamental mission of a great research university. So we're not just talking about the future of science, we're talking about the future of the research university, of probably education in general, but higher education. This is a report that I helped write through the National Academies about 10 years ago now, preparing for the revolution. We called it our 2x4 report. You know the story about needing the 2x4 to get the mule's attention. In this case, the mules were presidents and provosts of research universities. It had some effect, but again, I want to keep in mind the kind of things you are about here could have generalizable input. It's actually, I think, a mark of progress where a president of a major university, in this case, Terry Sullivan at University of Virginia, who's a good friend of mine, almost got fired for not being aggressive enough in adopting Coursera. We can save that conversation for another time. So as I've said now, although high-performance computing is an essential enabler of all that we're talking about today, I would really advocate that the term HPC should most importantly be viewed as high-performance collaboration. The emerging environments are built upon, and we have now with the emerging cloud computing environment and the next major shift in how we do computer architecture. I would argue that the fundamental pillars of the current paradigm for provisioning IT and communication are social, intrinsically social. So the idea that the computer is a social vehicle, unlike 20 years ago when we did UARC, is now fundamental. It's mobile, with many type of internet appliance increasingly, and very important to this community. They're sensor enabled. You know, our iPhones have accelerometers and GPS. It's just going to get more and more sensing capability in things we carry with us routinely. The cloud at various levels, not just as infrastructure a la EC2, but the cloud as platform, as a cloud as service. There's a lot of people now starting to think about science in the cloud and what that means. I don't know if you're aware that Google has just recently made a major announcement. They're opening up their platform for third parties, come all the way up the stack. They hope to create an environment in which e-science will be done within the Google platform. The whole big data movement and the cyber-physical sensor activators to couple the digital electronic world with physical platforms. So I would argue that these are the 5 pillars of the contemporary infrastructure. I was talking to some of you last night about how one of the things that NSF very much needs to do is to nurture conversation between the academia, funders, and the private sector. I think many of us think that the private sector is going to produce environments and tools and infrastructure that even the NSF is not going to be able to replicate and fund. And it also creates these cloud environments, create the platforms that allow for this broad and multiple use of these tools in ways that I've been describing. So we've got an emerging model of cloud platforms facilitated by global data networks with billions of endpoints, multifunction, multimedia, multi-sensor, connecting both people and physical world. This, I claim, is a new opportunity to actually create, propagate all quadrant knowledge communities, personalized learning environments, personalized medicine, connected learning and discovery. We're at a whole new era of these technologies having positive impact on the world. The digital age is the basis for the connected age. I've actually started talking about we're in the connected age. The fact that it's digital is actually a technical detail. The really important part of this whole new notions of connectedness that this world now brings about. And that this connected age is the basis for high-performance collaboration within and between knowledge communities. One of the best examples is the Nano Hub, and Clemic has done a marvelous job of quantifying the kind of impact that this has had on the conduct of this particular knowledge community. And I particularly commend a very brief TED talk that he gave recently, and that you consider in subsequent meetings having him come and give you the Nano Hub story, where he now can talk in very specific about criteria for success. I'm encouraging him to start trying to encapsulate what he's learned in ways that communities like yours can benefit from. So let's go back. Your research and education agenda: create and disseminate understanding, create tools, help mitigate or even solve major societal problems. But what about more? Creating and benefiting from a CI-enabled environment for your knowledge community, contributing to such an environment for the larger world of knowledge communities to support innovation in discovery and learning. I took my mother to the eye doctor yesterday morning, and on the door there, someone had stuck this, I took a picture of it: optimist, enrich the present, enhance the future, challenge the improbable, and attain the impossible. I would put myself in that category, and I'm hoping that you will, whoops, I don't know what happened, that you will join me as an optimist to try to achieve some of the potential of this new age. Thank you very much.
Have plenty of time for questions from the audience. First of all, thanks, Dan. Let's put our hands all together for this very inspiring talk from Dan. Thank you. Lots of time for questions. And wait for Mike.
Hi, thanks for the great talk. I'm actually very glad you mentioned clouds and their possible role in upcoming science discovery. Although not many people in the community believe that clouds are the future to go towards science. For example, the recent report from the Magellan report from DOE, at least, they weren't very enthusiastic about using clouds to replace the traditional computing infrastructure for science. I was wondering if you can elaborate a little bit on how, perhaps, NSF sees the roles of cloud for future science platforms.
It depends to some extent on what your aspirations are. If you are, well, I mean, let's see. It's well known, of course, that research computing, unlike in general enterprise computing, although I would argue those two things are getting more blurred, that there typically needs to be a better fit between the nature of the algorithm and the nature of the architecture of the underlying machine, and that it's less amenable to a one-size-fits-all kind of thing. So we have a spectrum of architectures that could be used for high-performance computing, particularly for modeling simulation, and now, of course, more recently, special architectures for data-intensive work and Hadoop environments and so forth and so on. So I think that idea of how general purpose environment you could need versus how much energy you want to put into a targeted specific application specific environment, all of the amazing things that this person was doing with GPUs out here, for example, will continue to be an issue. So there will certainly continue to be instances in which a tailored, personally application specific solution needs to be done. It also depends on whether you think the ultimate goal is a massive computing environment or an ecology for supporting discovery and learning of what I'm talking about. And it also depends on whether you're talking about the extent to which you're talking about the long tail of science, and that you aspire to create an environment that so for example, I would get every month the report of the people using the highest end TeraGrid machines and aspiring to use the Blue Waters machine. It was usually the same 12 people, okay? And there was a serious policy discussion, a very vocal policy discussion at the Science Board about whether NSF's role was to put hundreds of millions of dollars into the fastest machine for open science, even though only 20 people used it, or make an investment that supported a broader spectrum of needs. Okay, so I'm not claiming that the cloud and the tightly coupled kind of computing that certain fields require, fluid dynamics and others, don't necessarily map well into the kind of underlying environment that Google or Amazon runs. But I think, and it's also, I'm not advocating just the use of commercial clouds, I'm talking about multiple clouds, and I'm talking about interoperability between clouds, and I'm talking about private clouds, and so forth. My notion of supporting the long tail of science, of providing people in devices that they carry with them the ability to do computations that involve unimaginable amounts of back-end work that they're never even quite aware of, to have new forms of data-driven literacy. All of those things depend critically on the type of capability that we get through the emerging cloud environment, in my opinion. So I guess the short answer to your question is whether or not you think the cloud is important or not depends on what your goals are. And of course, we always have to recognize that there are, the phenomena of competency traps. The fact that certain entities have a competency in a certain way of doing things, and they don't have an interest in moving to the next form.
Thank you.
It'd be great to hear more thoughts and discussion about my assertions about the cloud and science.
Thank you for your very inspiring talk indeed. My quick question for you is, as you may be aware, that the higher education administration seems to me is going to another direction. That is a push for more commercialization for patents, a patented idea. In other words, the rewarding structure in higher education these days are still operating for the so-called closed science. Yeah. So as faculty members, I think we're all struggling this, the direction the scientific community is going on toward e-science, open science, but the administrators on each campus are pushing more for commercialization, protecting ideas. So can you share your thoughts on how we can better resolve this head-on clash?
Yeah. Well, I hope it can be resolved in a way where it is not a head-on clash. So first, let me say that, and there have been various references to this without using the phrase, I'm a very strong advocate of the Pasteur's quadrant model of research. That's this observation made by a former dean at Michigan Graduate School named Stokes some years ago as a critique of the model that Vannevar Bush used to start the NSF. And Bush had this classic linear model of curiosity-driven fundamental research being supported by the best minds. And then some of that hopefully would over time kind of migrate over into the applied side, kind of along the Department of Defense 6.1, 6.2, 6.3 kind of stuff. And it would eventually get over there and somebody would figure out how to use it and make it practical and make money out of it. And in fact, he advocated almost a big diode in there so that the needs of practical application did not come back and disturb the curiosity-driven thinking of the best minds, okay? And Stokes said, no, we really need to think about this as a two-dimensional space. So we have this axis is the extent to which something is contributing to application, a product, commercialization. And this axis has to do with the extent to which it's driven by curiosity and fundamental questions, okay? So up here we have Niels Bohr, I think he uses, a great physicist. And then down here we have Thomas Edison, who is an inventor. And then up here we have Louis Pasteur, who presumably made contributions in both important practical areas and in fundamental areas, and perhaps more importantly, built synergy between the two, grounded and informed what he did. And then the kind of impractical, unprincipled quadrant down here, he didn't put a name in there, but I thought of one later I'll tell you about offline. But so first off, application and fundamental discovery are not, can be done in a complementary way. But now your question goes beyond that, and it is, the pressure to patent, to license, to generate revenue that mitigates against openness and open science and so forth. So my personal hope at places like Michigan and Illinois and so forth is that although commercialization, tech transfer, well, let me first say that tech transfer through the route of patents and licenses and so forth is, to my mind, up to a point, a legitimate modality for transfer of information. I mean, it might, in many cases, be a much more impactful and beneficial than putting more and more papers into, an archival journal that a few people read. So it has a legitimate role within dissemination of results of research, but it can mitigate against openness. It can constrain academic value. So I think, first I want to say I think faculty such as yourself need to be actively engaged in these discussions, and you need to make sure people like Deb and Bob Easter and others are engaged in those conversations. You need to provide an environment that, for those who want to engage in that type of activity, there is a supportive environment for doing it. But it does not become a requirement for doing it, that it's the choice of the faculty member, that they're not. I'll also note that in my personal experience, the faculty that I've known at great research universities who have done quite a lot in the commercial side, I mean, people like Rob Rutenbar, the chair of CSE here, who's my doctoral student, are also terrific at everything else. So it's not that it's necessarily this against the other. So I think the continued push to open science, open data, open tools, open courseware, all of that is incredibly important and needs to be supported by the great universities. So the bottom line is this is a complex issue. It has multiple dimensions, and it, like many in academia these days, needs to be have constant discussion, oversight, and, as necessary, policy revision.
With regard to the four-quadrant model, I call it the interaction arrangement model.
Okay.
For 15 years, trying to think of the appropriate term
that.
for this.
Yeah.
And could you comment on some of the, at this point in time, maybe missed opportunities where a group like a community like this might look at some aspect of that quadrant and put some more energies? Obviously, the face-to-face and the different place, different time is big.
Yeah.
But the other two, seemingly, I've seen very little over the last 15 years in terms of real serious kinds of research to evaluate the character of the interaction and the type of knowledge production that might occur from such questions.
There was a report, very careful report done after the KDI initiative, which were intended to be, KDI was, I think a requirement was that it had to be interinstitutional. And Lee Sproul and Jonathan Cummings and some others did a retrospective study where they looked at, they did a reasonable measurement of the extent to which innovation came out of projects versus the extent to which they were distributed projects. And they actually found a negative correlation. In other words, the ones that were the most distributed were producing the least enterprise. And so initially I heard that, so, oh my God, that's the end of my whole collaboratory thing. And, so I've been, but when you looked at the report carefully, it was just to say that we're at a very, very immature stage of actually using this. And so the first part of my answer to your question is we just need to learn the stuff that we've already got. I mean, how many times do people engaged in just an audio conference call and people can't set it up, and people can't have the codes, or they get the time zone you're talking about, so all that kind of stuff. I have been, as chair of a new IT governance council for the University of Michigan for the past 2 years. I've been presiding over, among other things, the adoption of the Google environment for the University of Michigan, which we consider a very strategic investment. That's not just a new email system. I mean, we had 43 different email systems. We're going down to 2 now. And so that, the money people think that's wonderful. But the wonderful thing is this collaboration environment. And so I don't know, for example, how many of you have played with Hangout, the video conferencing capability within Google? So you can just set up a 10-way, and it'll be greater than 10, so a 10-way video conferences with shared documents with anybody in the world that has a Google account. And it works, okay? And I use it routinely now for staying in touch with my team. And one of the nice advantages is that we inherited a nice house on the west coast of Florida a few years ago, and in February, I work from there. But people don't know whether I'm in Ann Arbor there. I don't have on my Bermuda shorts and a palm tree in the background. I have, where I look just like I'm working from Ann Arbor. And I also, as a university level job, all over the campus, and we have 4 different campuses. So just using the stuff that we have now more routinely, and having environments where you don't just, we did General Motors some years ago paid us some few $1 million to analyze why their design teams distributed over the world, and with all this video conferencing stuff they'd put in, weren't getting anywhere. And the answer was pretty obvious after we looked at it, is that all they could do was sit and talk about doing work. They couldn't actually do any work because they didn't have the tools to actually do anything together. But the Google environment and other environments are starting to mitigate that against that, okay? So that's the short part of your answer. But more fundamentally, what I'm advocating is that we sit and look at the workflows that we are now doing, and think about that as kind of a state machine, then think about, well, what could we do differently? How could we transform this differently? And most particularly, if we do accept this notion that the same time, same place thing is the most precious, the most expensive, the one that's the most constrained, then how do we use the other 3 quadrants to improve what occurs when we do have the occasion to get together? Yeah, okay. Oh, okay.
Okay, yeah, I think I really enjoy your point about the high performance collaborations. And we see a lot of successful discipline to collaborate with the cyber infrastructure, like physics, biology. Yeah. But on the other side, did you see any other discipline has not very successful collaboration? And what's the problem or the failure, the reason? Because we as a GI science community, we just start to engage with those collaboration. How do we ensure our collaboration is sustainable, not just the 4 or 5 years project? So what's the lesson we can learn from those not very successful disciplines?
Yeah, there's several things embedded in your question. The first is that collaboration is, just having an environment for collaboration is not sufficient. Maybe necessary, but not sufficient. And ultimately, collaboration is sustained in academia and many other places through a relationship that produces mutual benefit. Okay, it's that you're getting something out of this, and then part of that, and for me, the UARC project was a landmark in my life for many reasons. One was that we had computer scientists and space scientists and social scientists working together, and after a while we looked back and said, we've done something amazing together. We could not have done separately. So once you have that experience in your career, it kind of becomes addictive and you try for more. So that's the first thing. And quite frankly, as I said before, there's this tension between the expectation of individual achievement of junior faculty for tenure and promotion and so forth versus collective achievement. My advice as a dean to faculty was to try to have a solo, clear spike of expertise and demonstrate ability to get funding for that work through NSF Career and others, but also to play some role in a collective enterprise in both. And then as you get further along in your career and achieve tenure and so forth, then you should, in general, try to spend more time in organizing and adding value for the collective good, and kind of keep that going. But the second thing I think is embedded in your question is an issue that I wrestled with all the time at NSF, and I'm sure they're wrestling with this. So we have these, 3 to 5 year projects. They create the incentive and provide the funding to bring together a collaborative team. They build an environment and do some amazing things, and then the money runs out. Okay, and then what? And so this notion of how to sustain success, and in the NSF story, and this is a constant discussion at NSF, we've got only so much money. What should be the ratio of sustaining infrastructure versus turning that money over to new discovery, okay? And that's a legitimate concern. And when I was there, the infrastructure, not just cyber infrastructure, but all the infrastructure, the ocean-going research vehicles and the respiratory facilities at Antarctica and all of that were pushing up to like 28-30% of the overall budget. Maybe that's too high. So another aspect of this enormous grand challenge that I've given you is to think upstream about this sustainability, about whether the sustainability could come through some kind of a consortial agreement, the extent to which you can get the universities to see the cyber infrastructure is so fundamental that it becomes part of the base budget funding process. Convincing universities, great universities like this, that they need to take on greater responsibility, for example, of data preservation. And your library here undoubtedly already has a large capacity in data stewardship. I bet they could take on some national databases at a marginal cost. So there's no unique answer, but that is a major problem, and you need to think about it from the beginning. Part of it might go to trying to commercialize things and generate a income stream that could come back and support it. Part of it could be trying to migrate it into an existing successful consortial agreement like Internet 2, get an infrastructure to be, they have this above the net initiative now. There's a lot of fresh breezes blowing through Internet 2. Another would be to migrate to the use of commercial commodity services. Another thing I want to say about the cloud question was, that I forget, the fellow from Harvard, he must be here, which is doing something amazing just as kind of a hobby by using EC2 and GPUs, okay? So this enabling people to do amazing things as individuals or small teams is part of the payoff of this kind of environment that we're talking about.
I have sometimes noticed when discussing many new exciting technologies, so many of things that, for example, Google is experimenting with or actually implementing, that people, well, both like just ordinary people, let's say my mom, or even like researchers in academic communities, that, well, some things are kind of part of, let's say, Google ecosystem, and some are part of Facebook ecosystem, and they kind of have trouble existing in both of them, so they miss some things there.
Yeah.
And they might actually kind of miss a lot of great things that are possible right now and today. And have you observed this, and what would be kind of a way around this problem so that the whole community would benefit of the possibilities we have?
Yeah. A couple of responses. The first is, I mean, the issue you described of doing something in Google, something in Facebook, something in this, something in that, is actually something we're wrestling with at the University of Michigan in the context of what's the future of a learning management system, okay? And I think we're starting to see, for example, in that arena, there's a system coming out called Canvas, which is basically a web services integrating kind of environment. So we're starting to see this level of abstraction where people are taking various web services and allowing you to tailor them and bring them together in kind of a mixed way, which in partly supports, I think, the kind of environment you're talking about. Another is that we've had the scarcity, you know, we run around talking about Moore's curve and exponential growth and all the technology and all of that, but the thing which has not grown, of course, is human attention. And I think we actually need a lot, and you folks actually could do something in this arena because of your visualization and data stuff. It's the question of the economics of attention. And how do we use these technologies to support the economics of human attention? And that's very, very fundamental issue that I think would be worthy of this community, and of you know, how could I more routinely see the activity space that I was a part of, and help me keep more balls in the air, and help me keep peripheral awareness of other things, and focus on what I should do here and there, and you know, things that go well beyond to-do list, and you know, what's the state of my world, and how do I engage when it kind of leveraging all of these kinds of resources.
Maybe just one final question, if you might have. All right. Let's join me once again. Thank Dr. Dan Atkins.
Thank you.
Honor.
Oh, wow. Thank you very much.